start now. Um, okay. So, hopefully everyone has at least. Okay, we have a very nice announcement. Uh, yeah, this is good. Um, okay. Um, so I hope everyone had a chance to go through all the homework. I think 8 people submitted, and there were like I don't know, 12 or more people in the classroom, but that's okay. If you don't have time to finish all of it, you can also still submit what you have, because again, points don't really matter. But it's obviously to your total benefit to submit as much as you can. Okay. Um, does anyone have any like I guess conceptual questions from the first homework they'd like to get out of the way? Because um, you can probably tell that the contents of lecture one are going to be quite fundamental to what we do moving forward.
I didn't completely understand how to do the last question about the unique existence, like the existence of a unique element in the set.
Let me take a look. Okay, so the idea here is that so by the way, I am gonna release solutions later tonight, so hopefully that will answer your question. But just in terms of how to approach this question, um, you want to think of this as how do you force this to be true? Um, what kind of restrictions do you need to put logically on the set or on the Boolean expression or something in order to make this exactly true? And it's good to think about kind of the counterexamples I was showing, like okay, if your class has 1 or 2 students or something like that, sometimes it helps to try and make examples and see if the logic you have written out so far works or not. And when you make counterexamples for why it doesn't work, that can kind of be instructive and tell you how it might need to change in order to be true. So obviously, this doesn't answer your question on how to actually solve the question, but I think once I release the solutions, it'll be more clear, and then feel free to ask then. We also have a ticket system set up. Uh, so there's like a ticket, what is it called, category in the server, and if you make, excuse me, if you open a ticket, what happens is it'll open a channel where the graders and I can see that you have a question, and then we can respond there, or you can
All
just ask
right,
in general, like
thank you.
yeah, yeah, sure. So let me share my screen. Any more questions, by the way, before we start?
Uh, for the question 3 for the modus tollens, I didn't understand how to do it.
Okay. Yeah. So again, the solutions are pretty much if you just look at it, you'll see what happens. But basically, um, there's always there's always a little bit confusion because it's really subjective uh to what it means to look like. But once you see that, you'll understand that modus tollens is actually the same exact statement as modus ponens. It's just for like I guess quality of life that we have two different ways of stating it. Okay.
I got another question.
Yeah, go ahead.
Um, this might be a dumb question, but like I didn't see in the document like what is the circle with a V inside thing called?
Circle with the what sign? Oh, the V?
Yeah, circle with a V.
Well, it's explaining it here, right?
Yeah, but like what's the name for it? Like is there something you
Oh,
call it?
oh.
XOR, XOR.
It's an XOR? Okay.
So so I didn't write this question. The instructor from last year, the guy who was lecturing, wrote this. And I don't know why he wrote it like this because I think normally you write it as a circle with an X on it or some other way. I haven't seen this circle be um what is this symbol anyway? Okay, this is just O times is what I'd use for XOR. I don't know. Anyways. OV. Okay, thank you, Paul. It is. The symbol is this. Okay. All right. Let's get started with the lecture now. So we're gonna be learning about sets. And sets are really nice objects, it turns out. They form the basis of how most people do math. And everything is a set. That's kind of the beauty of things. Um, Unless you do type theory, then everything's a type. But you know, different flavors. Anyways, so our definition of a set is going to be an unordered collection of items where each item appears at most once. So sets aren't going to have duplicates, and you can think of them as a bag of items. And this is a lie. So there's like that the barber's paradox. So the barber shaves the beard of every man who doesn't shave his own beard. So then, does the barber shave himself? Um, and either way you look at it, it doesn't make sense. So we also have this really weird looking set. So we say, okay, let's have A equal to every set where the set doesn't contain itself. So okay, is A inside of itself? Well, if A was inside of itself, then this wouldn't be true, so then A shouldn't be inside of itself. And if A wasn't inside of itself, then this would be true, so A should be inside of itself. So you get this like kind of weird thing going on. So one way you fix this in actual set theory is you say that okay, sets can't really refer to themselves when you're defining them. But it gets weird. Anyway, so yeah, so we're gonna run with naive set theory, and it turns out that for the vast majority of the math you want to do, you really don't care about like these kind of weird sets because this, for example, has nothing to do with the probability of heads or tails, right? Um, so you can, for the most part, ignore this weird stuff, and our definition is totally fine for now. Okay. So yeah. So ZF set theory is like the fixed version. So this is some German names. They fix stuff, and I think more commonly mathematicians will use ZFC, and the C stands for choice. Axiom of choice is added in, and you get nice stuff that's also kind of weird. Um, Anyways, so I'm sure you guys know most of these sets, but I'll just show you the notation at least. So we refer to the integers as this blackboard Z. So in LaTeX you use math BB, so BB just for blackboard. So you have this nice C. You have the natural numbers, so these are positive integers, so you go 1, 2, 3, blah, blah, blah. If you include 0 inside the natural numbers, you're very bad and probably French, that's not good. Q is the rational numbers, so the quotient of any two integers where obviously the denominator is non-zero. In some definitions of the rational numbers, you will say explicitly that every element of the rational number should appear in sort of a simplified form, right? You should have the GCD of the numerator and denominator being 1. Now the real numbers, they have a very complex definition. You would use something called Dedekind cuts to define the reals, and that takes a lot of effort, so we avoid that. And then we have some more fun sets. So we have the complex numbers, so you do something called adjoining. So you basically say, okay, here's a set of numbers I like, and now let's see what happens if I add this new element that has this particular property. In this case, we have the property that I squared is equal to -1. So if we do that, then we get the complex numbers. Finally, we have the quaternions. You adjoin 2 more elements, j and k, to the complex numbers, and you get h, and it's h and not q, one because q is already taken, and I think there's some mathematician Hamilton, probably, who found these numbers. Okay, so these are the vast majority of the large sets that you'll rely on frequently. Okay, so I'm sure that this isn't really confusing, so let's just move along. So let's talk about how sets can relate to one another, and the nicest way is subset. So A is a subset of B when, now let's read our shorthand here. For all x in A, x is in B. Okay? So we write this as A, and this symbol is subset EQ, B. Yeah, let me read this note first. So when we write subset EQ in LaTeX, we get this bar underneath, and this sort of gives the possibility. Yeah, thank you for that link. Yeah, this denotes the possibility that these sets could in fact be equal. But sometimes we want to say that these sets are definitely not equal, and then we might write it like this. However, there are some authors who will write this to mean subset EQ, so the convention is kind of not in a good place, but I think it's most clear if we differentiate like this. Anyways, so now that we have the definition of a subset, if every element that appears in A appears in B, then A is a subset of B. So now we can talk about set equality, and it's simply saying that A should be a subset of B, and B must be a subset of A. So two sets are subsets of each other, then they have to be equal. Okay, so does this definition make sense to everyone? So we can also think of it like the other way around, where, okay, let's say one of these two things wasn't true. So let's say A was not a subset of B. Well, how can we do that? Well, if A is not a subset of B, then it should be the case that this isn't true. So let's put on our negation hats, and we see that, okay, there should be some element of A where X is not in B. So if there's some element of A that's not in B, then definitely A and B aren't equal from our intuition, right? And so if we break this, then we can see that the sets aren't equal, and this by symmetry is pretty much the same exact thing. So hopefully that makes sense. So here's some nice examples of sets, and if you look very carefully, all of these sets are finite. So that's great. First of all, finite sets are very easy and nice to think about usually. So we have set containing the natural numbers 1 and 2. We have this weird looking set. It is the set containing the string code.pdf, the integer 15, and whatever this is. And then unfortunately, it turns out you can put kind of whatever you want into a set. So for example, in this set, we have the integer 1, and then now we have the set containing the integer 2. So, I mean, you may have noticed before when I introduced this bad guy that sets can contain each other, right? And in this case, nothing really terrible is going along because there's no weird contradiction or self-reference here. It's just a set containing a set. Here's the empty set, and here's the set containing the empty set. This is terrible. I'm not going to read this or anything. And this is fun. This is every set, which is a subset of this guy. So the empty set is a subset of this, and so is this set itself. And I don't think there are any other ones. And yeah, sets can be really ugly, it turns out, especially when they're infinite. So if someone says, here's a set, and you get no other information, you should actually be really afraid as to what's going on there. And so I was taking measure theory, and we were working with a particular set called R mod Q. This forward slash is read as mod, and it's really bad. So I kind of dozed off in the math lounge while thinking about it, and I woke up like in a cold sweat, and all I knew was that the culprit was R mod Q. So yeah, yeah, bad set, very bad set. It's the real numbers, but everything is really, really messed up. Okay. Any questions about sets so far? Remember, when I ask, just throw up your hand if you're typing a question so I know to wait. Oh, so we do have a question. Is there a functional difference between the empty set and the set containing the empty set? Well, they're completely different things. And how do I know that? I know they're not equal by our definition. So let's be careful here. So are these sets equal? So my first set is the empty set, and my second set is the set containing the empty set. So I noticed that this is not true if B is the latter set. So the reason is because the empty set appears as an element of the second set, but the empty set does not appear as an element of the first set. So these sets are different. They are definitely different objects. Okay. Let's move along. The power set. Okay, so we have this nice notation, this curvy P. This is known as mathcal. I think it's like calligraphy, if I'm not mistaken. So we do P of A, and this is the set which contains every subset of A. And we actually saw this before. It's this set here. So this set is exactly the power set of A. So let's have another definition here, the empty set, which I just used without defining, I'm sorry. We usually write it like this, var nothing. And it's the simple set which contains absolutely nothing. So let's talk about power sets. And there's a really nice concept from computer science which can help us think about this and also to manually generate these things, at least for finite sets. So, okay, let's have a set of size, a set A of size n, and now we want to consider some subset of A. So A here is the set that we want to construct the power set of. So we are going to represent B, which is some subset of A, as a bit string of size n. So a bit string is just a sequence of zeros and ones, and there's going to be n of them in a row. So first we need to assign some order to the elements of A. This is simple. You could sort them if they're integers or something like that. You can pick any arbitrary order. And then as we iterate through it, if we see an element and it does appear in B, then the next element in the bit string will be 1. Otherwise, it will be 0. So here's an example. Okay, there's a comment that's very hard for me to parse. If there is a set that contains every subset of another set, okay, so this would be a power set, then what's the difference between that set and the other set? So you, in parentheses, you've written since the original set contains all of its own subsets too, and that's not true. It's not true because, well, let's look at a simple example. Let's take the empty set. So the empty set is a subset of the empty set. Agreed? Because they're equal, right? Because these two sets are equal, then they both are subsets of each other. But the empty set doesn't contain the empty set. So the original set doesn't contain its subsets in general. So when I actually show you sets cannot have duplicate values because of our definition, each item appears at most once. Okay. So yeah, once I show you an actual example of a power set, it will be very clear to you what's going on. But let's talk about constructing everything inside here. So in this example, A is the integers 1 through 4, and B is the integers 1 and 3. So if we order these by sorting them in increasing order, then our bit string will be 1010, because 1 appears in here, 2 does not appear in B, 3 does appear in B, 1, and 4 does not appear in B, we have 0. So this is just saying telling you in order, does the element appear or not? There's 2 1s, so there's 2 elements. Okay. So now that we have this sort of relationship between a subset and this bit string, we notice that we can just iterate through all the bit strings of size n. So if I give you a random bit string, let's say 0011, then this corresponds to the set which only contains the element 3 because only the third thing is turned on. So now if we just loop over all the bit strings, blah, 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 we can generate the power set. Okay. I don't have examples of power sets, so let me just give you one. So let's say A is equal to this. So mathcal P of A is equal to, who wants to give this a stab? I have a big no. I don't know why. Where you would need a bit string across a set. So absolutely. So so the idea of a bit mask. So this is we in computer science we call this a bit mask. So the mask represents what's there and what's not. So for example, let's say you want to solve a Sudoku board, right? So you do something called backtracking where you go to the first position in the grid and you see all the possible things that are available, all the possible options that are still available. You pick the first one, and then you look at the bit mask, which corresponds to what's still available in that column, what's still available in that row, and what's still available in that 3x3 subsquare. And you would modify the bit mask and you continue in your backtracking process. And if you find that nothing works, then you go back and you undo all of your changes. So there's an example of where you would use a bit mask. Obviously, you can use structures such as like just regular sets in computer science, but bit masks do make things really nice. They also make things really fast too because you represent a bit mask with just a regular integer. So you could just use 32 bits and, for example, if you want to find the intersection of two things, then you could just and. You can use logical and between the two integers, and then you'll find the intersection. You can use or to find the union. I'm sure there's more examples I'm thinking of, but yeah, definitely a huge concept in computer science. Okay, so we have some guesses. We have some correct and incorrect guesses. So let's take a look. Let's do it like this. So we have this. So I'm assuming this was supposed to be a comma. So one thing I mentioned is that so a set is equal to itself, right? A is equal to A, which also means that A is a subset of itself. And so that should tell you that A also has to be an element of this guy, right? So I definitely need, so this is missing this, right? So we have two correct answers. And the next one is just a copy, so I'll ignore it. And yeah, so, and let's just look at the bit strings really quick. This is 0, 0. This is 1, 1. This is 1, 0, and this is 0, 1. So now you can kind of figure out that, okay, if I want to quickly generate everything, so first I have the bit string 0, 0, 0, so that's empty sets. Then I have 0, 0, 1, so that's just 3. 0, 1, 0, so that's just 2. 0, 1, 1, 2, 3. 1, 0, 0. 1, 0, 1. 1, 1, 0. And then, yeah, just everything. 1, 1, 1. And so let me double check. We have 1, 2, 3, 4, 5, 6, 7, 8 items, and that's the correct number. Yes, 2 to the n because every position in the bit mask has 2 options. Good. All right. So now I think power sets should be crystal clear. Let's move along. Union and intersection. So I mentioned these things, and now let me define them after having used them, as is typical. So you can define this using a set builder notation, which I think is pretty nice. And union is very similar to disjunction. So if I want to union A and B, conceptually, by the way, this is saying add together the sets A and B. So anything that appears in either one should be in the union. So yeah, it's every element X such that X is in A or X is in B. And now intersection is very similarly defined. I basically copy and pasted. And instead of disjunction, use conjunction. So intersection requires that elements are in both of the original sets. Okay. So if you want to think of this as a Venn diagram, let me make a thing. Right. So yeah. So if we had our sets A and B, right? We use a smaller size thing. A, B. So the union would be this, everything like this. And the intersection would be just this. Okay, we have a question. So the vertical bar is /mid, and the colon is literally just literal colon. Are they interchangeable in set builder notation, I assume? So I'm a stickler for always using the bar. You can use the colon. I'll obviously know what you mean. So I guess they're interchangeable, but I do prefer the bar. Okay. So I think union and intersection, because we know Venn diagrams, pretty straightforward. So now let's talk about something interesting. Yeah, so let A and B to any two sets. They can be infinite or whatever you want. And we're going to talk about first their intersection is going to be a subset of A. So this is a nice statement. So how do I show how do I show that this is a subset of A? Well, I have to go back to my definition of a subset. That's the only way. That's the only way I can show that something is a subset, at least with the tools I have right now. So I need to show every element that appears in the first guy has to appear in the second guy. Okay, well, okay, does every element in here appear inside of A? And so this is a statement, so everything in here appears in here, blah, 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 blah. Right, so we're going to learn our first kind of baby proof method. It's not going to be super rigorous, but we're going to do something called universal instantiation. So I want to prove this. So whenever I want to prove a for all statement, I basically I see this variable comes from a set, and I just will it into existence. And now I have some x to play with. So it's kind of like, if you're writing a program and you declare a variable and now you have it to play around with. The difference, I guess, here is that when I do this, I don't know anything about this x. It could be any element as long as it comes from here. So I don't know anything more about it than just that. Okay. And apparently I'm doing magic now. I just need to show that this statement follows. And in this case, that statement is simply x is inside of A. So, okay, I have this element. I need to show it's inside of there. Okay, blah, blah, blah. Okay, so this is how I'd actually write the proof. So this statement will do my universal instantiation. And then I use my definition of intersection. And I know that this has to be true, right? Because I go up here and I see that the intersection is every element such that this is true. Okay, so that means, okay, this is true. But if you guys did your homework properly, you would know that if this is true, then x has to be an A. So we have the conclusion, which is what we wanted, right? We have this. So what we did was we just started from an arbitrary element in here and concluded this. So the proof is done for this part. And it was very simple, right? And now we'll see a very similar proof. So you can probably get the logic. So we want to show that for every x inside of this set, that x ought to appear in here in order to show this subset relationship. So I say, okay, let x be in A. And then if x is in A, then it's definitely true that x is in A or x is in B. And therefore x is inside of this set. And okay, that's pretty much exactly what I've written here. So yeah, nothing crazy is happening, but this idea of universal instantiation, dealing with the variable after you've seen this for all quantifier. Okay. Let's just do another one. So now we're dealing with the power set of A, and we want to show it's a subset of the power set of A union B. Okay. So now we should think a little bit more carefully. So I want to do universal instantiation, and now I'm used to the drill. So I will instantiate an element inside of here. So suppose big X comes from the power set of A, and I'm using big X now because we'd like to use capital letters for sets. It just makes things a little bit easier if the variables are sort of more conventionally named. So yeah, X is some set that's inside of here. Now, by definition, the power set of A is every subset of A, so X has to be a subset of A. And now we use the statement we just proved. X is a subset of A union B, right? We have this, right? So if X is a subset of A union B, then that's exactly the same as saying that X is an element of the power set of A union B. Okay? So I started with this, and I ended with this. So I proved that for all statement that shows that this is a subset of that. Okay, any questions about how to do these subset proofs? So you should notice that they all follow the same format. If you want to show A is a subset of B, instantiate something in A and figure out how it could be in B. How are we doing on time? Okay, we're about 35 minutes in. How much is left? Okay, not too much. Let's continue. Set complements. Okay. So when we talk about complements, we have to have some idea of a universal set. So maybe we're talking about the integers, and then we would talk about the complement with respect to the integers. But normally in mathematical literature, we wouldn't really do that. We would just be able to assume what we're going for. Um, okay. So what do I have here? Right. So why do I? Okay. So B here is my universal set. So it's basically everything that doesn't appear inside the set we're talking about, but does appear in the universe. So we're gonna use we're gonna use this as our universe for the moment. So this is more of a computer science definition. This bracket n. I believe I've seen this notation used elsewhere to mean something else, but I've more frequently seen like in algorithms, for example, that you really care about sets that look like this. So I will use this definition. It's just the first n natural numbers. And so now we're going to use this as a universal set. So in this case, B is going to be the first four natural numbers, 1, 2, 3, 4. And if we want the complement of this set, 2, 4, we can, okay, we obviously see that the complement is just 1, 3, right? Those are the only elements that aren't in here that are inside of here. But if we look at the bit string, right? So the bit string for A with respect to B is this, right? So we have the second and fourth bits on. And now the complement is just what you get by flipping all of the bits in the bit string. So that's nice. It's a cute little thing. Okay. Okay, now we have de Morgan's laws as promised for sets. And if you actually, I'll come back to the comment later. Sorry. But yeah, so let's say again we have some universal set U. Now, if we want to talk about the complement, so before we talked about negation, right? Negation with disjunction. Now we're talking about the complement with respect to union. So if we take A union B, but we complement it, it's actually the complement of C intersected with the complement of B. So I think a picture is nice here. So well, let me bring back these guys. Okay, so let's look at this very carefully. So A union B complement. So what does this look like? So first of all, this is A union B, right? And so the complement of that. So let's say the entire grid is our universe U, right? So the complement of A union B is all of this. Now, I've just noticed that there's a phone. I can start a voice call in here. Wow, that's neat. Okay. Anyways, so we have the complement of A union B, and now how can it possibly be equal to this? That looks quite weird, honestly, even in my opinion, after seeing it many times. So let's look at first A complement. Sorry, the complement of C. Sorry, the complement of A. Okay, I said that wrong. So the complement of A is this, right? So it bleeds into B, which is not what we want. We want to sort of get rid of this area inside of B. And how do we do that? We're going to intersect it with the complement of B. So by intersecting it with the complement of B, we note that everything that's in the final set can't be in B because it's in the complement of B. So that sort of erases the part inside of B. And so after doing the intersection, I get precisely what I wanted. It's the complement of A union B. And this isn't really a proof because I've just drawn a bunch of squiggles all over in Paint. But you can, of course, sit down and prove this. And I think I hold you at gunpoint and ask you to do so. Yeah, okay, you guys are going to do this, so I'm not going to show you how. All right. So any questions about complements, unions, intersections, and whatnot? No? Okay, very good. Okay, so now we're gonna do something tricky, so now it's really time to pay good attention. So we can union a finite number of sets together, and we can also union an infinite number of sets together. And when I say infinite, I can also mean the bad kind of infinity, like the really, really big kind of infinities. but maybe not too big because I don't know about really, really, really big infinities. But that being said, we're going to use regular infinities, the size of the natural numbers, for example. So let's talk about an indexing set. So the most common indexing set that you guys are used to is the natural numbers. And of course, you're used to seeing a series, right? So we have this index here, right? I. So we talk about A1, and then we have, okay, A1 is equal to 2, A2 is equal to 4, A3 is equal to 8, and so on. But the point is, this I came from some set. But it could have come from any set. In this case, we use the natural numbers, but what if I wanted to use the integers? And so I could get something called a double-ended series. So I would have A0 is equal to 1, A minus 1 is equal to 1 half, A minus 2 is equal to 1 quarter. There's nothing wrong with that. The question is just what indexing set do I want to use? And then we have the idea that, okay, we don't have to just have numbers as a result of this index. We can have whatever we want. Okay. So in this case, we have big A sub I, and this is a collection of sets. I think the proper terminology is that you want to call this a family of sets, and this family is indexed by I. Okay. And so we have this family of sets indexed by I. You don't know what it looks like yet, but if I want to do a union across everything, I can do something called an indexed union, and it looks like this. So it's every A that appears in U. What is going on here? Yes. So it's everything that appears in the universe, as long as there is some index in my indexing set where A belongs to the set from the family of sets indexed by that I. That was a mouthful, but the point is that an element ends up in the union as long as there was some set in the family that supported its existence. Okay. So let's actually look at an example. So let's define one family, and this is a very simple family. So AI is the set containing simply 2i plus 1. So it has only one element. So every single AI has only one element. And our indexing set is going to be the natural numbers, right? So that's going to be 1, 2, 3, 4, blah, blah, blah. So what is the indexed union of all AI when we have this indexing set? Does anyone want to take a stab? Move this over. This is going to be C dot, and to do braces in LaTeX, you have to use backslash brace. The odd number is very good. Right, so let's examine this carefully. So when I equals 1, oh no, something bad happens and I'm forgetting that. Right, so it's almost the odd numbers. But when I equals 1, we get 3. Yeah, so 1 isn't in here. And we can prove that, right? So let's go back to our definition here, right? So let's look at 1. 1 is inside of our universe, let's say. There's no I such that 1 is inside of that thing, right? Because that would imply that 1 is equal to this for some I in the indexing set. So if I had 1 is equal to this, I would have 2I equals 0, so I equals 0, but 0 is not a natural number. And we have a French person in chat, and they're going to be banned from the server very shortly, unfortunately for them. But yeah, so it's almost odd numbers. Almost. It's this, right? Right. Now, I should probably make fewer mistakes. So now what happens when we use, what about when I is equal to the integers? What will I get then? So the positive and the negative odd numbers, and we can just call that the odd integers. Okay. Oh, I actually missed the previous answers. Anyways, um, where are my things? Okay, here. So what about when uh, I is equal to the rational numbers? This one's interesting. Okay, so quick answer is saying simply Q, and that is correct. So now we really have to stop and think, because this is not trivial, right? So, okay, so what I'm saying, right? What I'm saying is that this thing, this thing is equal to Q. Too lazy to replace everything before. So how do I show that they're equal? Well, I have to, every time I want to show set equality, I have to show subset in both directions. Okay, so let's think. Okay, so let's say I pick something inside of here. So I'm gonna do my so when you want to write set equality proof, and do I have any in here? No, I don't. So that's not good. I have no set equality proofs. That's terrible. I should change that for next time. Okay. So yeah, it's just two subset proofs, but it's good to see how it's done. So, um, so let's call this first set X. Okay. This is a bit of abusive notation, but whatever. So I want to first show that X is a subset of math Okay, so how do I show that? So let little x be inside of X. Okay, great. So if I know that there's some element inside of here, then this has to be true. So then there is some I such that X is in a and I is in math and all of a sudden VS Code has determined that I'm writing in LaTeX, so that's cool. So yeah, so there's some I inside math and this is weird. Normally I is just like an integer, but now it's a rational number. So so now this is true, but AI is equal to only one element. It's just 2 times I plus 1. So therefore, x is equal to 2 times I plus 1. Okay, and now I know that x must be a rational number, because if I multiply a rational number by 2 and add 1, then I still get a rational. Okay, so I've done one direction. Let me do the other. Okay, so let x in mathb be q. So I know it's a rational number. So the point is I want to show that it's inside of this. So that's a little bit more difficult. So I want to, so sometimes when you're doing a proof like this, you have to kind of know the answer ahead of time. So it helps to do a little bit of scratch work. So if I think about it, right, what is going to be the index that this x appears in? It comes from basically this formula. So I'm kind of just solving for I, right? So I care about x minus 1 over 2. So now pick and this. So after I've done this calculation, I'm gonna write this. Now pick I is equal to this. So this kind of is what happens in proofs. Sometimes we have this magic number coming out of nowhere, but it just solves everything. So then it's clear that x is in a sub I as yeah, I mean, you do the math backwards. 2, let me just make sure I got it right. Times I, yeah, plus 1 is equal to x. Thus, we found some I such that uh, basically this, right? So x is in big X. Okay. So yeah, that's basically the essence of how you write these kinds of proofs. Any questions about what we did? Getting thumbs up, and looks like everyone's on board. Great. So let's move along. Um, okay, Cartesian product. This is a nice thing. So it's basically saying, the Cartesian plane is an idea from this. So it's basically saying you have two sets, A and B. Now give me all pairs of elements where the first element comes from A and the second element comes from B. So this is the formal definition. It's every pair A comma B. A is from A and B is from B. Okay, and you use this backslash times to get this nice character. Okay, so yeah, something funny happens now. When you talk about A times B times C, if you have a third set. So notice that normally you might write A times B times C without any parentheses. Uh, but this operator isn't exactly associative, right? It matters what order you do it in. And the problem is that if I do this, right? So if I do this, my elements look like A comma B. But then if I multiply it, if I do Cartesian product with C, right? Then I end up with this. I don't end up with triples, I end up with a pair, where the first element is a pair and the second one is like a single element. But we just do a little bit of abusive notation and abracadabra, we have just this kind of thing, right? We create n tuples. My call is over in 10 minutes, but I think we can finish in 10 minutes, so that's fine. Okay, so yeah, let's talk about the real numbers. So when we talk about our Cartesian product with a set and itself, then we might just say squared. Nice. Oh, sorry, I just saw a question. Is this the standard procedure for proving that they are equal? So I'm assuming you're talking about this, right? And yes, this is very standard to show two sets are equal. Like this is pretty much like the main technique. The only other way you would use really is like you would end up trying to prove something else, which indirectly shows this by means of some lemma or theorem that you still have subsets. But yeah. Okay, so yeah, when we say R2 like this, we mean our Cartesian product with itself, and that's the Cartesian plane. Brilliant. Those all pairs of real numbers. Okay, and I'm sure this is a simple concept, just pairs. We have the cardinality of a set. So it's the number of elements it has, and there's something interesting that goes on here. So when we talk about cardinality of a set, I'll write it like this, right? And what you get out sometimes looks like a natural number, sometimes it's some kind of infinity. But what's really going on is that the output is called a cardinal number. And so when we talk about cardinal numbers and how they relate to one another, it's really not the same as when we talk about just, for example, naturals. So I say, for example, the cardinality of the empty set is 0, but this 0 is a cardinal 0. It doesn't work exactly the same. Keep this in the back of your mind because later on when we get to functions like injections and surjections, we're going to see why comparing cardinal numbers is something completely different from comparing natural numbers with each other. Okay, so yeah, so the cardinality of the empty set is 0. It has 0 elements in it. And a set with n numbers in it, like we mentioned before, has a power set with 2 to the n elements in it. Okay, so last thing we're going to talk about. Oh, we have our hand raised. We also have a question in the chat. So let me answer the question first. For the Cartesian product, is the set all possible combinations, or is it just the pairs of? Okay, so it's the first one, right? Because I've done sort of I haven't ordered the elements first of all, right? So I don't have a notion of the first element of A or the first element of B. So yeah, it's going to be all possible ways to pair these things up. Yeah, now go ahead, Josh. Oh yeah, so your question in chat is the cardinality of the set containing the empty set 1? And the answer is yes, because it has exactly one element, which is the empty set. Okay. That also has cardinality 1. Good. So for anyone watching on YouTube, he asked about the set containing the empty set. So we have this, and that's just 1. And why? It's because it contains only one element, which is the set containing the empty set. And I mean, if we just replace this with any other thing, right, we would notice that its cardinality is obviously 1. If we just did, right, it doesn't matter what thing it is, as long as it's any element. Okay. Okay, so infinite sets. What how do we talk about cardinality or power sets or anything? So it gets complicated. But we have something really nice to talk about, which is Cantor's theorem, which is basically saying that if you take the power set of a set, then you get a cardinality which is larger. Now remember, sitting in the back of your head should be the fact that this comparison between cardinal numbers, again, is not like normal integers. So it does kind of work out. It does work out the same way, but for completely different reasons that you can compare them like this. So for finite sets, this is really easy to talk about. So you pick any number, any non-negative integer, and then you get this, right? So to the n is greater than n. You can prove this. It's very simple. So Cantor's theorem is obviously true for finite sets, but for non-trivial, for the non-trivial case where we have infinite sets, some very spooky stuff is going on, and basically you can always make bigger and bigger infinities as a result, right? So the point is, okay, let's take the natural numbers, and I say, okay, this isn't infinite enough for me. So I take the power set of that, and I've gotten a set which is definitely bigger in some sense. This infinity is bigger. And this infinity is actually the same infinity as the size of the real numbers. But I can go a step further. I can take the power set of that, and I get a bigger infinity, and I can do this as many times as I would like. So just something nice to think about. You can always have really, really big infinities, and so on and so forth. Okay, any questions? No? Okay, great. So I just scroll through this homework real quick. Let's see if there's anything I shouldn't mention. Yeah, here you're asked to compute some indexed unions and intersections. I think this is a nice problem. Problem on the complement. Cartesian product, power sets. This one has a very strong record of tripping up people, so be careful with this. Yeah, this is oh, hang on. What's going on here? We have the symbol that I didn't define for you guys. How'd that happen? Oh, I just totally skipped over it. That's really funny. Okay. Okay. Yeah, set difference. That's an important thing. So let me just hold your attention for a moment longer. So you write A set minus B like this. So the backslash is set minus, the forward slash is mod, and the forward slash you're not going to see in this class or for some amount of time. And it's literally just saying, okay, take everything out of A if it was in B. So everything in A as long as it's not in B. Yeah, that's so weird that I totally skipped this. So yeah, if you have A equals 1, 2, 3, 4, and you have B equals 3, 4, 5, 6, then if you do set minus, you get 1, 2, because 1 and 2 are the only elements in here that are not in here. And if you do the subtraction the other way around, then you see that this 3, 4 is in here, but the 5, 6 is not, so you get this. Yeah, prove this subset, prove this set equality. So remember, for equality, always do both directions. So we have a definition of symmetric difference. This is an interesting thing. If you're curious on the Venn diagram, it looks like this. This is symmetric difference. So it's saying to prove this. Sorry, no, it's saying, okay, yeah, you have this definition, and then prove this equality. So there's basically two ways to define it. You just have to show that they're equivalent. This is a really nice looking question. It has a slightly tricky answer. And this is a very difficult question. So I definitely only even read this if you've done everything else. But basically nobody should expect to solve this question. Historically, no one has solved it because there's like one tiny thing that's really, really hard to get a grasp of. So yeah, don't spend too much time on this. Okay. So any final questions? No? Okay, all right. Thank you everyone for coming and have a great day.
Thank you.
Thank you. Have a nice one.
You too.
Thank you.